we move on to the second topic for this chapter. Okay. In this course, we consider optimization in n-dimensional Euclidean space. Okay, so that means the vectors we are considering here are vectors in Rn space. Okay, and also all the norms, the involving norms, are for vectors in the Rn space. Okay, as everybody already knows, what are the vectors in Rn space? Do you? So the vectors in Rn space is the n-tuples of an n-tuples, right? An n-tuple of real variables. Oh, sorry, real numbers. Some people might, okay, so we write, okay, I'll write it on here. So X is a vector, x1, x2, up to xn, right? So here we adopt the column vector notation. If you are dealing only with vectors, no matrices involved, then you can choose either to use the row or the column vectors representation. But if you have to involve if you have some matrices involved as well, then that means if your vector has to multiply with the some matrix, then I think you have to make sure that, okay. So to be safe, I use only the column notations. You have to set a system for yourself, otherwise you will confuse yourself. Okay. So here so here I always use the column vector notation. Okay, and there are another version that if you adopt the row vector notation, then I think something the results may not be the same. But you have to consistent with what you have, because at the end, if you are consistent with it and it's correct, then the end result is the same. Okay, once we have, okay, so what is the norm? When we have the vector, the norm, roughly speaking, norm is something that we use to measure the length of a vector, or the size of the vector. Some people call it the length, or some people call it the size of a vector, right? But the thing is that norm is not unique. This is so in the slide you can see that in okay, these are the definition of norm. This is the definition of a vector norm in Rn space. This is the definition of norm in general. So if you have the norm in Rn space, if you have norm in the function space, or if you have a norm in a different vector space, this is the standard definition of norm. Okay, so norm is a real value function of the vector, of a vector x, right? Which satisfy the three properties. The first one is, okay. The first one is the norm of x is a non-negative number. It cannot be negative. It's a non-negative number, and the norm is 0, or the length of the vector is 0 if and only if x is a 0 vector. If x is not a 0 vector, then the norm must be positive. Okay, that's the first property. And the second property is that the second one is called scaling property. The norm of a scale vector, okay, the norm of alpha x, where alpha is a scalar. The norm of alpha x is equal to the absolute value of alpha multiplied with the norm of x. Okay, it has what we call this is scaling property. And the last one is the norm must satisfy the triangle inequality. That means the length of the sum of two vectors cannot be greater than the sum of the length of the two vectors. Okay, so norm of x plus y must be less than or equal to the norm of x plus norm of y. But you see, when we say the formula, this is the mathematical formula. But then, but if you want to say that in the language that people can understand, then we say the length of the sum of the two vectors cannot be greater than the sum of lengths of two vectors, right? And norm, okay. So there are many types of okay, and so norm has many okay. Norm is not unique, as you can see here. I give you the definition of what we call P norm. Okay, the P norm of a vector x, and we used the subscript. Okay, we use P as a subscription of the norm to denote this is the P norm of a vector x. So P is a real number. Actually, P can be a 1 to P is a real number. I think P is a real number. P is from 1 to infinity. Notice that P can be infinity as well. Okay, P can be a real number, which is okay in the closed interval from 1 to infinity. And there are three most common norms that we use. We use one norm, or two norm, and infinity norm. So P, the most common value of P that we use for norm is 1, 2, and infinity. And this is quite, I think, sufficient in applications. But each of them have different interpretation, different meaning. When we use the one norm, then you see that in the equation 2.3, the one norm of x is equal to the summation of the modulus of xi. Okay, it's the sum of the sum of the modulus or the absolute value of each component of the vector, and this is one norm. And then for the two norm, I think probably this is the most the norm that we the norm that we get used to most, right? This is the two norm. Actually, this is the actual length of a vector, right? And this is why some people call it a Euclidean norm, because this is the length in the Euclidean space, the actual length, right, of a vector. And this is infinity for infinity norm. The infinity norm is the maximum of the absolute value of the components of x, of the vector x. Right? So when if you use, so when you are dealing with norm, you have to specify which type of norm you are using at the beginning, because sometimes some results doesn't hold for any value of p. It may be true for the two norm or one norm or infinity norm. Okay, so we have to, when you use that, because okay, you have to be careful. You have to specify which type of norm you are dealing with at the beginning. And then if you don't, and after that, then if you use the norm, and then that means this is the type of the norm that you are mentioning at the beginning, right? In this way, we don't have to write the subscription. We can lighten the notation by we can drop the subscription p, right, in the notation. Okay. Now sometimes, okay, we find that we want to know the angle between the two vectors. How can we know what is the angle between the two vectors. If we have vectors, right? The two vectors, then we know the two vectors from the formula of the dot product, right? Because from the dot product, we know that the x transpose y the dot product between x and y is equal to the 2 norm of x times the 2 norm of y and multiply with the cosine of the angle theta, right? And from this, then the cosine theta is equal to x transpose y, right? Divided by the 2 norm of x divided by the 2 norm of y, right? And you see that x transpose y is what? X transpose y is equal to the summation of xi, yi, I from 1 to n. This is straightforward, right? When you do the okay. And when the angle between the two, and when the angle theta is equal to 90 degrees, then we say the two vectors are orthogonal. I think usually in geometry, when we look at the angle, right, in geometry, then we usually use the words perpendicular, but in linear algebra, we usually use orthogonal. Okay, when the two vectors, okay, if the angle between the two vectors is 90 degrees, then we say the two vectors are orthogonal. Okay, or x is orthogonal to y. Okay, and the cosine theta is 0 when x transpose y is equal to 0. Right? If the dot product is 0, then that means the two vectors are orthogonal. And we have a useful inequality, which in which we if we want, okay, we are in, if you want to know the upper bound of the absolute value of the dot product x transpose y, then we use the Hölder inequality. Okay, the Hölder, this is a German name with the two dots on top. Is the U with umlaut. Is Hölder's inequality, but if you pronounce it as normal English, then some people usually call it Hölder's inequality. But actually, the German pronunciation is Hölder. It's not with the O sound. And the absolute value of x transpose y is not greater than the n norm of x multiplied with the m norms of y, where the numbers m and n are related by this equation 1 over m plus 1 over n must be equal to 1. So that means if n is equal to 1, then m must be infinity. Okay, and when m is equal to 2, then m must be 2, according to this equation. So that means when m and n are 2, then we have a special name we call Cauchy-Schwarz inequality. This is the special case of a Hölder's inequality. And I think in our chapter, when we prove a property of a variable metric of the DFT of the equation Newton, you will find that we use this inequality to help us. For the okay. Okay, now we look at the definition of linear independence. Okay, for linear independence in Rn space, then if we have a set of vectors, okay, when we have a set of vectors, when we have okay, where the number of vectors x, okay, k is the number of the vectors we are considering, and k cannot be greater than n, right? This is from the second year linear algebra, because the number of independent vectors cannot be greater than the dimension of the vector space. The number of the maximum, okay, the number of independent vectors cannot be greater than the dimension of the vector space. The dimension of Rn space is n, so that means in Rn space you cannot have a set of linearly independent vectors more than n. Okay, and so a set of vectors x1, x2 up to xn is said to be linearly independent if the solution, this is okay, if alpha 1 x1 plus alpha 2 x2 plus alpha k xk is equal to 0, implies that each scalar alpha is equal to 0. Okay, this is what we write, but actually what the meaning is that this one is when you look at this, right? This statement alpha 1 x1 plus alpha 2 x2 plus up to alpha k xk is equal to 0 vector gives you a homogeneous solution, or gives you a homogeneous equation in the value in the alpha 1, alpha 2 up to alpha k. Can you see this, or can you remember this? Okay. You agree with me? No or yes? Thanaporn, you remember this? Hmm? On the left-hand side, when you rewrite it, right? A matrix multiply with the vector alpha 1, alpha 2 up to alpha k is equal to 0, 0, 0. Don't forget when we write this, what? How many equations? You see that we have the summation of this, but each vector xi is has the size dimension is n. So this one must be n by 1. Right? It's n by 1. 0, this is the n vector. Okay. And this for this matrix is equal to x1. Okay. Is the augmentation of the vectors x1, x2 up to x. Okay. So this matrix, what is the size of this matrix? This size of the matrix is we have n row and k columns. N by k. Where this one is k by 1. And this is the n plus 1. Okay. So actually this is in fact when we write alpha 1 x1 plus alpha 2 x2 plus up to alpha k is equal to 0, then actually this is a homogeneous equation. What? It forms a homogeneous equations in the variable x1, x2 up to xk. Now we come back to our slide. Okay, so that means if a set of the vectors is said to be linearly independent if the solution of the homogeneous equations is a trivial vector or is a zero vector, right? If alpha 1 up if every alpha I is 0, then this set of this set of vectors is linearly independent. Otherwise, it's linearly dependent. Okay. So when we talk about linear independence, this is what we call dichotomy. There are only two cases. You know the meaning of this? Dichotomy. Dichotomy means it can be only two possibilities. We have okay. Regarding linearly independence, we have only two possibilities: independence and dependence. Nothing else. Okay. And now we move to matrix. Here we are interested in matrix because what? Why we are interested in matrix? You will find that in solving optimization problem, you will deal with matrices and sometimes, okay, and also linear equations, linear algebraic equations. Okay, so we use quite a lot of backgrounds from the second year linear algebra. And first we look at the matrix rank. Rank of a matrix is the maximum number of linearly independent columns or rows in the A matrix, right? But how can we know that A is? How can we know that the columns or the rows in A are linearly independent? So that means you have to solve. You have to test linear independence. And by doing this, we are solving linear equations. So what is the algorithm we use to solve the linear equations? We use a Gaussian elimination, right? We do the row operations. We apply row operations until the associate until the matrix we are considering is in echelon form. Is in echelon form. Well, so to find the rank of A, then we so you have to if you want to know the rank of A matrix, then you have to do the row operator. You have to apply. You have to do elementary row operations until A is in echelon form. Okay. So we carry A to A prime, where A prime is an echelon form of A. Okay. Then the rank of A can be determined very easily from the number of the non-zero row in the A prime. And okay. Now we move to the eigenvalues and eigenvectors. In optimization, in optimization, eigenvalues and eigenvalues and eigenvectors arise when we consider some property of a matrix. Okay, you will see that very soon, late after this. Okay, and but here we just review what are the definition of eigenvalues and eigenvectors. So the eigenvalues, we look at for A is a square matrix. Okay, we assume that A is a square matrix. Then if there are the scalar lambda and a vector x satisfy Ax equal to lambda x, then the lambda is an eigenvalue of the A matrix of A, and x is an eigenvector of A. And if A is n by n matrix, then how many eigenvalues and how many eigenvectors we can have? Then we know that from the eigenvalues can be computed by solving this equation. Eigenvalue of A is okay. The eigenvalues of A are the solutions of determinant of lambda I minus A equal to 0. And this equation is known as the characteristic equation, right? Characteristic equation of A. Okay. The determinant of lambda I minus A is equal to 0 is called a characteristic equation of A, right? And you see that this one actually yields is identical to a polynomial lambda n plus so actually this one is a polynomial of degree n, right? We can prove this. This is a polynomial this is a polynomial of degree n. So if because the characteristic equation, I'm sorry, the characteristic function is a polynomial of degree n. That means if A is an n by n matrix, then there are n. The matrix A has n eigenvalues, whereas okay, and each eigenvalue corresponds to an eigenvector. But for each eigenvalues, there are an infinite number of eigenvectors, but we choose only one of them. This is enough. Okay, I think that's the. Now we look at the positive definiteness property of a symmetric matrix. Okay, a positive definiteness involves a symmetric matrix. If we don't mention symmetric matrix, and you should know that the implication, okay, you should know this implication. If you don't mention this, but because the positive, as you can see, here in the definition, it involves A transpose AX, right? When A is not symmetric, then we still write an equivalent matrix, right? So that X transpose, okay, so that B is and B, if A is not symmetric, then we can find another symmetric matrix, which for which X transpose AX is equal to X transpose BX, where B is a symmetric matrix. So what we are concerned is this quantity, this quadratic function. Okay, and so normally, but okay. So the a symmetric matrix A. Okay, A is a square matrix. Again, it's a square matrix. A square symmetric matrix A is said to be positive definite, or PDF for short, if X transpose AX is always positive for any non-zero vector X. Here you see that in the definition, we exclude zero vector, right? Because it's obvious when X is a zero vector, then this one must be zero. It cannot be greater than zero, right? So, okay. And then similar to this, then we define a positive semi-definite. When we have the word semi comes in, then okay, then the quadratic function X transpose AX is allowed to be zero. So we write, okay, the A is said to be positive semi-definite, or PSDF, if the number X transpose AX is non-negative for any vector. Now, because here you don't have to exclude the zero vector, it makes sense. Because here we allow this to be equal to zero as well, right? So in the definition of positive semi-definite, we don't have to exclude the zero vectors. Okay, and this, I think similarly, we have also a negative definite and negative semi-definite. Okay, but we just look at that by yourself. But in our lessons, we are using only positive definite. Okay, if you convert, if you change the positive to negative, then you have the definition of negative definite. Okay, and then if you change from the greater than or equal to zero to be less than or equal to zero, then you change from the positive semi-definite to negative semi-definite. That's all. Okay, but there is another one that I need to mention here, which is indefinite. Now, the positive and the positive and negative definite are not dichotomy, because there are all these are not a dichotomy, because there are more than two cases. You have positive definite, negative definite, and indefinite. So what does indefinite means? A symmetric matrix A is indefinite if the number A transpose AX contains positive and negative values depending on the vector X. You see that in the definition of the positive definite, right? The quantity X transpose AX is always positive. So that doesn't mean it doesn't. Okay, the sign. So the sign of X transpose AX doesn't depend on the value, or doesn't depend on the vector X. This is a property of a matrix itself. Okay, but when this doesn't happen, then the matrix is called indefinite. So it can take the positive or negative value. Okay, it can have depending on the vector X. This is indefinite. Okay. Now, how can we how can we given a matrix, how can we know that it's positive definite or negative definite or indefinite? You see that from the definition. The definition is useful. It gives us the meaning, right? It gives us a meaning, but in this case you will find, and also in many there are many cases in which the definition is useful, but is not. But we cannot prove. But we cannot use the definition to prove it because it's not convenient. Now look, I'll explain more to show you. Okay, to clarify what I mean. You see that this one a positive definite. A is a positive definite if x transpose A, x is positive for all zero vector for all non-zero vector x. So what is the number of the what is the number of all non-zero vectors? Infinite. There are an infinite number of non-zero vectors. So if you use this to prove if you have to use this to show, to test the positive definiteness, then this is impossible because the thing you have to test, you have to test according. If you use this statement, you are dealing with an infinite number of objects. You cannot do that within a finite time. Okay, so the method, a pretty standard method in mathematics is that we have to replace this by an equivalent statement, and the equivalent statement can be used in the test, right? And now you will see what it is. Now we have this result. Okay, we'll go right to this proposition. Okay, the proposition 2.3.7, right? A matrix A, a matrix A is a positive definite if and only if all its eigenvalues are real and strictly positive. So you see that all its eigenvalues of A are real and strictly positive is a necessary and sufficient condition of A being positive definite. Right? All the eigenvalues of, so that means if you rephrase this proposition, then you can say a necessary and sufficient condition for A to be positive definite is that all the eigenvalues of A are real numbers and strictly positive. Now you see when if A has n by n dimension, then you can see that A has only n eigenvalues. And nowadays you can computing eigenvalues is no longer difficult. You just go to MATLAB and you type use the function EIG, right? And then you have all the values of the eigenvalues. Okay. And then you know that. And then and a matrix A. So you see that a matrix A is positive definite if and only if all the eigenvalues of A are real and strictly positive. And similarly, A is positive semi-definite. A is positive semi-definite if all its eigenvalues of A are real and non-negative. So if some of the eigenvalues of A are 0 and the others are positive, then A is a positive semi-definite matrix.